So Exascale, a long look at Lustre limitations and alliterations. So first question on your mind is, what's with your title, right? Limitations, Lustre doesn't have limitations. What's Lustre scale today? There's a little bit of agenda. Maybe we'll just skip right over that. Exascale differences, and then a bunch of individual items on what exactly are the problems with Lustre going to the next levels of Exascale. So, what's with your title? We all know that Lustre is fantastic, right? It's perfect. Biggest, baddest file system in the world, 7 of the top 10, petabytes of storage, terabytes a second of performance. Yes. Can we do that easily, every time, repeatedly, with no effort? No. It takes a lot of effort to do the large-scale installations. We know that every time we try to get the next larger system out there, we're going to spend a lot of extra effort working at it. We know that there are going to be problems, and we expect that, and frankly, that's why everyone pays big bucks for Lustre support. All right, so fantastic. How are we going to get to Exascale? Exascale is bigger than all of this, bigger than all of the present systems by a significant factor. 10, 20, 50 times current petabyte sizes, but also 100 times, 1,000 times current performance sizes. All right, so why Lustre limitations, and why not Lustre solutions for Exascale? Well, I don't have the answers. I'm going to try and point out some of the problems, and there are some ideas for some answers, for some ideas for going forward, but not all. Here's a fun graph of Lustre systems over time. Sorry, they're a little bit hard to read, but 2004 in the bottom left and 14, 16 on the end. You can see it looks like the way I drew my arrow, which was arbitrarily, that, oh yeah, sure, we'll get to Exascale. But I could have easily drawn a different line that kind of curved off asymptotically towards whatever. So that's where we're at today. Maybe future systems that are planned are actually tend to fall off this arrow a little bit. All right, so what are differences for Exascale? The first is hardware-based, right? So we have hardware scaling when we get bigger and bigger systems. We have many more components. Those components, in turn, imply many more failures. Also, larger scale systems imply larger and larger timeouts, and I'll talk about that in a second. You will have, as you have bigger network systems, you have more network losses associated with that. You also, when you have larger systems, you have more hardware diversity, right? So you have many more components, you have diverse components that leads to more complexity. In addition to hardware scaling, you have software scaling, right? So your software layers now are going to be increase the complexity of your system as well. So if you're talking about things like adding HSM systems on the back end and burst buffers on the front end, or PLFS, or all these other things, you're adding extra layers of software. Also, with increased scale becomes more common occurrences of what used to be corner cases. Your corner cases all become common at scale. So all of this kind of leads together to an increase of complexity of the system. So as I said before, you have increased component counts, you have increased software layering counts, you have increased interactions between components, increased interactions in software layers, and cascading events because of that. Also, you have a much more difficult time figuring out what's going on. You have no visibility into your system as it gets larger and larger, or the visibility becomes more and more difficult, let's put it that way. Recovery. Okay, so I said timeouts increase with scale. Why should that be? Well, because, as I said before, corner cases become common at scale. Your if you have a standard deviation of operations, as your sample size gets larger, the number of outliers, the items on the far ends of your probability curves are going to occur more and more often. So because of that, those are normal operations, right? So you have your timeouts are set in Lustre to cover normal operations. That's the whole point of the timeout is you're supposed to be able to detect abnormal operations. But as your asymptotes head off towards infinity of normal expected operation times, those timeouts are going to have to continue to increase to cover those worst cases. Lustre has a feature called adaptive timeouts. Fantastic. It helps to find those limits. So it operates such that it actually just times the amount of time operation is expected to finish. So that's fine. It'll find out. It'll find the ends, but that you still don't get to not wait for those ends. You still have to wait for those full lengths of those adaptive timeouts. The adaptive timeouts will just be bigger. You also have temporary outages in a lot of systems that will become larger and larger with scale. So Cray used to call them beer timeouts, where the network would kind of disappear for a little bit. They would go out for a beer, come back, and by that time the network would be kind of back up. So as the scale increases, again, you're going to have to wait longer and longer times for these queues of stuff to kind of work themselves out. The second issue with recovery is that your recovery actions are tied to these timeouts, right? So that now that these timeouts are bigger, your recovery, and this is not necessarily Lustre recovery, where the Lustre recovery process after a failover, but just normal expected wait times for recovery actions. So a resend, right? That's not a recovery. Well, it's not quote unquote Lustre recovery, but it is a recovery action. And those events will have to wait for longer and longer times, again, to cover the normal operations. Related to this are the increasing components and the increasing of failures, right? So we have more components, more drives, servers, network packet loss. So these things together, increase in failures, plus the increase in time to recover for these failures, is going to result in real problems. So these are bad trends, right? So that's adding together increased failures and longer times. This is going to be more and more problematic. Availability. So with a large enough scale of a system, you're always going to have an OST down at some arbitrary scale, right? So what does Lustre do when the OST is down? Well, you don't have access to your data. Is that okay? No, it's not, right? It's simply not okay not to have access to your data. As your systems get bigger, you'll lose access to more and more of your data. So what do you do about that? Well, I know, let's use fewer OSTs, bigger OSTs. Let's use ZFS and have gigantic OSTs. Okay, that works. You have fewer OSTs, the chances of them going down are lower, potentially. Couple of problems. There's first of all, as your OSTs get larger and larger, your chance of RAID rebuild goes up, right? There's a larger chance of one of those drives is going to fail. The bigger problem with that is that this is the wrong kind of scaling, right? What you're saying is you're admitting that Lustre is not going to scale with the number of OSTs. Instead, let's use fewer OSTs. Let's avoid the exascale problem by using vertical, more expensive, gigantic OSTs rather than horizontal scaling, where you're distributing your data more widely. So there's actually potentially a solution to this, which are RAID-style layouts, right? So right now, Lustre does RAID 0, basically accounting on the subsystems underneath the local file systems to provide redundancy. But that's a problem because if your OST is down for whatever reason, the power goes out to the OST, failover doesn't help, right? So the data is simply unavailable. Drive, whatever, enough drives are dead. So the way you get around that is by having a network-based recovery. So a RAID system, PD RAID system, RAID 6 system in the network such that you can actually recover when a physical rack is dead, when a physical OST is dead. We don't have that today, but potentially that can be built into Lustre's layout system today. Also, our current limits, the most OSTs that anyone's ever done are in the order of thousands. The actual maximum limitation on the number of OSTs is 65,000. Well, okay, that's 65,000 sounds a lot bigger than 1,000. Maybe we can get there, but I think there's already problems with having OSTs in the thousands already, and so we need to address those issues that are already there, that are well known. Network issues at Exascale. So LNet messages are FIFO'd, right? So there's a when you add a router in particular in the way, the messages coming through the router are just simply the ordering of the messages that are sent from the clients and collected on the router. Servers have some ability, potentially, with the network request scheduler to order the requests they get, but only if they actually get those requests. If they're backed up behind routers, it can do nothing about it. So what happens is you have a server that has some messages. Today, they're simply processed in first come, first serve order. And if a request can't be processed, or if it, for instance, something's waiting on a lock, or if there's a backup of requests to disk, then the threads all just sit there sleeping on it. If you've ever looked at your threads on your MDS or OSTs, most of them are sleeping. They're all waiting for disk IOs. And what that means is there's a few threads running, hopefully, but potentially, if you get enough, the right ordering of requests, they'll all be sleeping. And the server could be processing requests that are actually useful. It could be processing pings and lock cancellations and all sorts of stuff like that. It could be doing that, except that all threads are sleeping. There is the high priority queue, where you have one meager thread trying to answer all the requests that are still pending, if the server can actually get to it, but that's kind of iffy, and it's a flaky kind of area. And I actually think I'll talk a little bit more about that later. We also still have one-to-one client-to-server pinging. So every client pings every server, every OST. As we heard yesterday, Fujitsu turns it off because they can't handle it at today's scale. So at Exascale, it just gets worse. So we need to get rid of that. There are potentially lots of ways to do that, but we still need to do that. And then the final point here is that Lustre itself is simply not robust in the face of drop packets. We heard that from Cray yesterday. There are some items that are not resent. There are cases when whatever response, request is dropped that basically ends up resulting in a deadlock. There's plenty of them that we've found. I'm sure there's plenty more to be found. All right, hardware diversity. So, Lustre is a file system, but it's not a disk, well, it is. It's a disk system, right? Lustre is a hard disk-based storage system, right? It is, but what Lustre doesn't do today is deal with media other than hard disks, right? But there are other media than hard disks, right? There's flash, there's RAM, there's disk, there's tape. Well, tape's relegated to HSM. Flash is relegated to who knows what, burst buffer or whatever. RAM, well, there's a little bit of caching in Lustre, but it's not really considered as part of the storage system. So Lustre today basically has no idea of hierarchy. It has no idea of the ability to, the idea that there are potentially tiers of storage, economic tiers, performance tiers, and there's OST pools, but it's not a significantly advanced enough in order to be useful to kind of deal with things like automatic migration between tiers, and to understand that there's differences between media types. You have to, predetermine where data is going to live in your system. Also, the Lustre today is a completely client-server model, right? That means that you can't use potential resources that are available on your compute nodes. So compute nodes today have lots of RAM. They may very well have flash. They may have hard drives. Lustre can't use any of that. And that, I believe, needs to change, right? Fundamentally, your scaling of your system scales with the number of clients. And you don't want to have to match the number of clients with some number of servers per client. What you want to do is be able to utilize the resources that are available. So a little bit more on servers then, servers in particular. Servers have lots of cores. They have lots of memory, lots of power. And Lustre today runs as a threaded model, right? So there's a thread per request. A request comes in, a thread is dedicated to handling that request that comes off the top of the queue. So what's the right number of service threads that there should be running? There's a formulaic computation today that's based on the amount of RAM and the number of cores. That's some number. You get up to whatever, thousands, but that's about it. So on the order of 1,000. And most of those threads aren't doing anything. They're sleeping, they're consuming resources, switching between threads is expensive. You have to do paging, you have to do cache line flushes. This is not particularly a efficient way of handling requests coming in. Also, you have fairly big problems when the number of requests coming in is greater than the number of threads. As I said before, I mentioned the high priority queue. It's supposed to deal with situations in which all threads are sleeping, so there's supposed to be one thread left over to be able to handle high priority requests like lock cancellation, so that disk I/O is banned from that thread. But the problem is, first of all, it's only one thread. Second of all, this is rarely, if ever, tested. We don't typically test with very large number of clients that are greater than that 1,000 number of threads, and that's really the only time that high priority queue really gets exercised. There's existing bugs that are related to that. So what's a potential solution to that is replacing this thread per request model with a CPU localized state machine. So that means you take a request, each request gets formed into its own state machine, and CPU localized threads run continuously, moving items from state to state until they block, in which case it drops that thread and then drops that request, picks up the next request and starts processing that one. So in other words, these threads now that are localized to a CPU keep running. So the threads keep doing useful work, and it's the requests themselves that wait. They're not the threads that are waiting on requests. Software stack. So right now we have a pretty deep storage stack already, right? So just for instance, just on the OSD, we have the OSD itself, the software there sits on top of another file system, LSFS, ZFS. You have layers of block layers. You have RAID layers. All these things reorder, do different caching algorithms. They not collaboration, concentration, integration, whatever. Adding requests together. All of these things add up to basically inefficiencies in the storage stack. Maybe we can get rid of this with, I don't know, a direct OSD device. So we have an OSD that eliminates this intermediate file system in the middle there, the local file system, and writes directly to disk. Maybe gets rid of some of these problems. Also, above this, on the client side, there's large software stacks. So as I said before, there's no tiering inside of Lustre. So what is the way to get around this? We add other layers. We add PLFS in front of Lustre. We add burst buffer in front of Lustre. We add HSM system behind Lustre. So all of these additional layers just add to this software stack complexity. So that software stack complexity means that you have a much greater integration effort, you have much less visibility, you have questions about the handling of recovery, about the handling of transactionality through all these different layers. And then the question is, well, who do you blame when something goes wrong? If you're a system integrator, if you're the guy that put this, system architect, whatever, the guy that put this thing together, the guy that gets blamed is you. All right. So visibility, I've mentioned this a couple of times. Sadly, you can't see my background of Lustre log messages. It's too faint there, but you've all seen Lustre logs. You know that they're quite opaque, impossible to kind of understand at first glance. You have to really dig into them. It's not fun these are being sarcastic, clearly. No one loves system debugging. It's impossible, difficult to even collect logs across very large systems. As we get to exascale, this log collection operation is just going to become more and more of a pain. When Lustre fails, Lustre's all kernel modules, so Lustre fails, your node goes down. So you have kernel dumps, system panics. It's very difficult to even get those out of there because your node is dead. So you have to have mechanisms to collect these logs. All of this increased complexity just in collecting the logs. Now you need to actually understand what's going on in the logs, right? So you have to, basically need an expert in order to understand all the different log messages, what's going on, how to correlate all of the information in here. Also, typically, you don't even turn on debugging until after there's a problem because Lustre debugging is heavyweight and uses additional resources, storage resources, slows down your servers. So you don't even turn it on until after you see a problem, in which case it's too late. Or you hope that you'll see another problem again similar to it soon because you don't want to leave all this stuff on while you're waiting for the event to happen again. So I don't have a good answer for this, but what we need is a full-time, machine-readable, centrally collected, zero-impact debug data that we can look at to understand what happens when there's a problem. Lustre HA. So HA is somewhat of a misnomer in terms of Lustre HA. It's generally a separate system that is a kind of a gross system. So it has basically one option, which is when it decides there's a problem, it kills a node, fails over, you start a new node. So there's no finesse in there. Everything's a sledgehammer, right? Sledgehammer solution to everything. Kill it, shoot it in the head, start it up on a different server. So you lose all of the potentially all of the information that was on the node. It takes you a long time to recover. We talked about recovery time before. As things fail over a lot, this whole system will start to grind to a halt as we get to more and more failovers. There needs to be a better, finer-grained, and a less of a single answer for all potential problems in Lustre. There needs to be a mechanism to understand what actually the state of the cluster is. So rather than waiting for timeouts, saying, and upon a timeout, deciding that a client is not there, evicting a client, there needs to be kind of an external, up-to-date idea of what the actual cluster state is. We shouldn't be sending blocking RPCs to a node that we know is down. We shouldn't be waiting for it. We shouldn't make anyone wait for it. We should just move on, evict it immediately, and we should know the state of the cluster external to trying to find it out within Lustre and without having the system in a real-time situation. All right. Oh, and final point on here is that for dual-ported, RAID redundancy or dual-ported redundancy, dual-ported redundant access to your data, a lot of times there's two servers that are connected to the same storage. Well, as many of us know, there are situations in which your HA system is not perfect, that you actually might end up starting two nodes simultaneously that are both accessing the same drives, which ends up in data corruption, which is not a good idea. Okay. One of my last things here is Lustre Code. So the fun movie on the side, and I apologize that my titles out there aren't quite big enough to read. This is a movie of Lustre Code check-ins. I uploaded it to YouTube. You can watch it later if you want to. So this is 2002. Moving forward, you can kind of watch the check-ins. So Lustre was this movie started in 1999. Lustre was designed for petascale originally. That was the goal. The goal was never to get to exascale. The petascale was a stretch. And there has been lots of revision over time. So as you can watch in my fun movie, now we're up to 2003. As over time, we've added features, we've added stability, and we've added complexity, right? So Lustre gets more and more complex. A lot of times these changes to Lustre have unforeseen consequences, right? We don't know what a change is going to do, and that is partially because of this increasing complexity. So at this point, at today's Lustre, I don't believe that anyone has a full view of everything that's going on in Lustre anymore. Even Andreas, the world's expert, the leading expert on Lustre in the world, I don't believe, and Jan, he can argue with me, that he knows all of what's going on in Lustre anymore. Another problem kind of related to this is poor documentation. We've complained about this for a long time, for many years. It's still true. There have been various attempts to try and fix this, but I believe it's still true that our documentation is not sufficient in order to describe all of this different complexity and all these different, these all, by the way, every little dot here represents a file. So you can see these files are there's a lot of them. 2005, by the way. And so as a result, because no one has the full picture anymore, because there's a large number of files, because of the poor documentation, there's a lot of old code, a lot of cruft that is there, and it's very difficult to get rid of. So Intel actually on the OpenSFS contract did some work to try and remove some lines of code, and I believe they have, but I also believe there's a long way to go. 2007. I'm going to move on because I'm done with my slides. Sorry, you can watch the rest of it on YouTube. I'm trying to move on. There we go. Okay. So what am I going to do about it? What are you going to do about it? There are substantial problems. Today, Seagate is mainly working on stabilizing Lustre for our current large-scale customers, right? So we have a lot of, we're a victim of our success in some ways, right? We've sold a lot of systems. That means we have a lot of customers, and customer support is high touch. Sad to say, for Lustre, we have a large number of demanding clients, and we spend most of our time fixing problems in current releases. So in a sense, this is only fixing symptoms, right? It's fixing symptoms of foundational problems, and we need somehow to address the fundamental foundational problems. And so that leads me to question whether we've reached at this point, at this level of scale, not exascale, but at today's level of scale, whether we've reached that saturation point. That's it. Oh, well, actually, it's not quite it. I'll show you my other graph. I added a couple of things on the end. Well, I don't know. Maybe this is the direction we're going. That's it for you.
So, I agree, I don't understand everything. Eric understands LNet, and I stay away from that. Anyways, you know, none of the problems that well, maybe not none of the problems, but many of the problems that you discuss are not insurmountable problems.
I agree.
Right? And so, you know, I would be happy to see, you know, Seagate working on some of those issues. Right?
I agree. There are absolutely, I don't think any of these are insurmountable, but it does represent a significant amount of work, I think, to address them all.
Yeah.
And we don't have a lot of time to do it. And you know, this is the community, and yes, if we had infinite resources and you could hire, Seagate could hire as many people as we wanted to work on this, and I would be, you know, I agree. This is how we make money. We sell Lustre, and we need to be able to, you know, continue to sell Lustre. So yes, I don't think that we're in disagreement that this is the end of Lustre. What I'm saying is somehow we need to move away from our current. So Intel focuses mainly on developing new features, I think. We're much more focused on, as I said, trying to keep our current customers happy, address the issues that we're actually seeing in the field. And somehow we need to move back and get more towards these foundational issues.
So beyond doom and gloom, do you see, you know, a road forward here, or what?
Yeah, so there are potential solutions. I mean, that you know that have been proposed. I don't know. You know, there are answers for Exascale that don't involve Lustre. That don't involve Lustre as a primary storage system. It is seen as a tier, and there are other layers put around it, as I was saying. So path forward has burst buffer. Lustre is relegated kind of a second level. It's considered a lower performance tier. Same thing with Fujitsu. They have a flash system in front of Lustre. Lustre is one part of it, and they have a larger scale HSM-based storage system. So maybe that's the role that Lustre plays, and maybe these issues don't need to be addressed as the single, all-consuming Exascale file system. Maybe that's the answer. I don't know. Maybe Eric has a better answer. His talk is up next.
Yep. One more question, I guess.
Thank you for the presentation. We have discussed yesterday for a long time. However, maybe let me just show some noted. So our experience is 10,000 OST works. However, some I already talk about that. There are so many memory consumptions increasing by the number of OSTs. Also, maybe we have some 90,000 client and 2,500 OS. So that works. So however, some difference. So maybe you mentioned about how have recovery time and timeout problem. So many problems. So we need to fix how we should do Lustre.
How do we fix?
Yes.
How do we fix
How
the
do you think
timeout
about
problem?
Yes.
I don't know how to fix the timeout problem. I think that's.
Yeah. So how Seagate will do?
Yeah, I don't have a good answer for you today.
Do we have time for another question, Stefan? Do we have time for another question?
Hi, Nathan. So it seems that we don't have any future. No, I'm joking. I think that Lustre is one of the problem for the Exascale. For me, two are the major problem. One is the POSIX, because POSIX is not an Exascale interface. So basically, the work that we do for the fast forward is moving from POSIX. Another thing is spinning disk. I'm sorry to say that, but it's not possible to have millions of spinning disk in order to sustain 100 terabytes per second. It's not more possible. I don't know if this is part of the exascale problem or not, but this is the reality.
Yeah, it is part of the problem. That's what I was saying, that we have to understand that a storage system is made up of not just spinning disks, but all sorts of media. And we need to be able to take those different media's different characteristics, their latency, their speed, their capacity, their cost, take all of those things into account when we're designing systems and when we're using systems.
So this is why Lustre has several problems, because we are playing with POSIX and we use mainly spinning disk.
Yeah.